Hello and welcome to this lecture on design of singly reinforced and doubly reinforced beam for the course title Reinforced Concrete Structures Design and Drawing. This is our lecture number 4. So in the previous lecture we have discussed about the design of singly reinforced beam. Today we are going to discuss about the design of doubly reinforced beams. So a singly reinforced beam has a limiting moment of resistance based on the limiting value of steel. If the applied moment is larger than mu limit, that means the permissible limit, two alternatives will be available. So either we can increase the depth of the section or we can provide a compression reinforcement. So in the previous lecture we have discussed about a singly reinforced beam section. So this is an example of a singly reinforced beam section where we are providing AST, that is area of steel in the tension zone. So this is a singly reinforced beam. When is it a singly reinforced beam? When the section has a limiting moment of resistance based on the limiting value of steel. That is a singly reinforced beam. However, if the applied moment is larger than mu limit, then we need to have some provisions. Either we increase the depth of the section, which may not be economic, or we can provide some compression reinforcement. So by the term compression reinforcement, it means to provide some steel in the compression zone. So we already know if this is the beam, this is a simply supported beam and there is a loading from the top, the beam is going to bend. So when it bends, there is compression in the top fiber and there are tensile stresses in the bottom fiber, right? So therefore, if we look at the beam cross section, this is the compression zone and below it is the tension zone, right? So we have already discussed these points in the previous lectures in the philosophy of design of beams. So we are going to provide compression reinforcement. In many cases, the depth of the section is limited or restricted due to architectural and other considerations. So it is not feasible always to increase the depth of the section. In that case, there is a one and only one alternative, that is to provide compression reinforcement, which leads to a doubly reinforced section. So a singly reinforced section has a limiting value of the moment of resistance based on the limiting value of steel. When the moment applied is larger than the moment mu limit, then we can either increase the depth of the section or we can provide some compression reinforcement. However, it is not feasible to increase the depth of the section. That's why we are going to provide compression reinforcement or steel, which is leading to the formation of a doubly reinforced section. So let's compare the cross-sectional area of a singly reinforced beam and a doubly reinforced beam. So if you look at the figure, so this is the neutral axis. So when we talk about the neutral axis, this is the compression zone above and there is a tension zone below, right? So when there is reinforcement in the tension zone, it is called a singly reinforced beam, and when there is reinforcement in the tension as well as compression zone, it is called a doubly reinforced beam. So you can look at the figure, there is something known as compression steel. So that is the basic difference between a doubly reinforced beam section and a singly reinforced beam section. So we have provided steel in the tension zone as well as steel in the compression zone. Therefore, it is called a doubly reinforced beam. So let's look at the stress block diagram. So this is the compression steel and there is tension steel. This is the effective depth, small d, and this is the width. D dash is the effective cover for the compression steel. So looking at the strain block diagram, the ultimate strain in the steel is greater than equal to 0.87 Fy by Es plus 0.002. And your strain in the compression zone is maximum is of 0.0035. So the total compression stresses in the compression zone is 0.36 FCK XUB, and the total tensile stresses in the tension zone is 0.87 Fy AST, where AST is the area of tension steel and ASC is the area of compression steel. So a doubly reinforced section will have compression reinforcement at a depth of D dash below the outermost compression fiber. So we have already looked at the strain diagram, where AST is the total reinforcement at the tension phase and ASC is the reinforcement in the compression side. XU is the depth of the neutral axis. CU is the compressive forces in concrete, the total compressive force in the concrete, which is equal to 0.36 FCK XUB. CSU is the compressive force in the compression steel, and that is FSC into ASC. What is FSC? Let's look at FSC is the design stress in the compression zone read off from the stress strain curve corresponding to a strain of epsilon SC in the compression reinforcement. Epsilon SC is the strain in compression reinforcement, that is 0.0035 XU minus D dash by XU, that is 0.00351 minus D dash by XU. So this is the total strain in the compression steel. So the total compressive force Cu is Cu plus CSU, and that's equal to 0.36 FCK XUB plus FSC into ASC. When we talk about FSC and ASC, this is for the compression side, the area of reinforcement in the compression zone. The total tensile force is 0.87 Fy AST. To locate the neutral axis, we equate the compressive force to the tensile force, that is Cu is equal to Tu. So we equate the two equations, we get 0.36 FCK XUB plus FSC ASC, and that is equal to Tu, that is 0.87 Fy AST. So on equating the two equations, we are going to come up with the depth of the neutral axis. XU is the depth of the neutral axis, so we can get the value for depth of neutral axis. So what are the types of problems that we'll be coming across for doubly reinforced beams? So first type will be determination of the moment of resistance when material properties and sectional properties are given. That means the material characteristic strength and sectional properties, that is cross-sectional area, is given. The second type of problem would be determination of actual stresses in the section subjected to a given bending moment. So a bending moment will be provided. The third type involves designing of a given section to resist the given ultimate moment. So these are the three types of problems that we are going to solve for doubly reinforced beams. So determination of moment of resistance. So case 1, when XU by D is less than the limiting value. So XU by D is less than XU limit by D. In this case corresponds to an under reinforced section. So when XU by D is less than the limiting value, it is called an under reinforced section in the working stress method. In this, the moment of resistance will be calculated by this equation, that is mu is equal to 0.36 FCK XUB D minus 0.416 XU plus ASC FSC D minus D dash. That is the moment of resistance calculation for a under reinforced section where XU by D, depth of neutral axis, is less than the limiting depth of neutral axis. When we say limiting depth of neutral axis, it refers to a balanced section. So when the neutral axis depth is raised above, that means it is a under reinforced section. Coming to case 2. When xu by d is equal to the limiting value. So we have already discussed that when xu by d, the depth of neutral axis, is equal to the depth of neutral axis, then it is called a balanced section. So xu by d is equal to the limiting value, that is a balanced section in which the steel reinforcement reaches its yield stress at the same time when the strain is reached in the concrete. That in a balanced section, the steel and the reinforcement are going to yield or reach its ultimate capacity at the same time. So moment of resistance mu reaches its limiting value, that is mu limit is equal to 0.36 FCK xu limit b into d minus 0.416 xu limit plus ASC FSC d minus d dash. So this is the equation for mu limit. By mu limit we mean it is the moment of resistance of a balanced section. The third type is when xu by d is more than the limiting value. The moment of resistance of such a section will be limited to mu limit only. We cannot exceed the value of mu for a case where xu by d is more than limiting value. We have to restrict it to the balanced moment of resistance, and the section should be redesigned. So a section cannot have a moment of resistance more than the limiting moment of resistance, which corresponds to a balanced section. In such a case, we should redesign the section. So a doubly reinforced section is required when the applied moment is greater than the limiting moment. So MUA is greater than MU limit. So when MUA is greater than MU limit, then we require a doubly reinforced section. The difference between the applied moment and the limiting moment, the difference between the applied moment, that means MUA minus MU limit, is carried by additional tensile reinforcement, that is AST2, and compression reinforcement ASC. So the difference between the applied moment and the limiting moment is carried by an additional reinforcement AST2 and a compression reinforcement of ASC. Thus, a doubly reinforced section is equivalent to a singly reinforced section and a balanced section and a section with additional tension and compression reinforcement. So let's look at the cross section and the stress strain diagram. This is the doubly reinforced beam section. We have AST and we have ASC. D dash is the effective cover for the steel in the compression zone from the top fiber, and B is the width of the beam. XU max is the limiting depth of neutral axis. This is AST1. So when we consider a singly reinforced beam, this doubly reinforced beam can be divided into two parts. That is, the first part, which has AST1, is called a singly reinforced beam. It is equivalent to a singly reinforced beam, and this is the stress block for a singly reinforced beam. Plus, it has an additional reinforcement with ASC and AST2. So there is extra reinforcement in the tension zone as well as there is extra reinforcement in the compression zone. This additional steel plus a singly reinforced section is going to give us something equivalent to a doubly reinforced section. So a doubly reinforced section comprises of singly reinforced balanced section plus a additional reinforcement AST2 in the tension zone and ASCE in the compression zone. So the net effective compressive stresses is CSU, and the net effective tensile stresses is 0.87 FY/AS T2, and this is 0.87 FY/AS T1 for the singly reinforced section providing AS T1. This is the stress strain block diagram for a doubly reinforced section. So ASC is the compression reinforcement, and it is obtained by the clause in page number 96 in IS 456-2000 code book, where mu minus mu limit is equal to FSC ASC into D minus D dash. FSC is where design stress is compression reinforcement, and ASC is the area of compression reinforcement. D dash is the depth of compression reinforcement from the compression face. So we have seen in the diagram, this is the compression reinforcement, this is the tension reinforcement. So this is D dash, the depth of compression reinforcement from the compression face, and this is the ASC, or the area of steel in the compression zone. AST. Calculating AST, the total area of tension reinforcement shall be obtained by the following equation, that is AST1 plus AST2. So we have already seen in the diagrammatic representation, AST is the total area of the tensile reinforcement. AST1 is the area of tensile reinforcement for a singly reinforced section for mu limit, and AST2 is the area of steel for a doubly reinforced section where there is a compression reinforcement. So ASC FC divided by 0.87 FY, that is the value of AST2. That is the additional reinforcement in the tensile zone. So let's look at a problem on how to solve problems on doubly reinforced sections. So determine the moment of resistance of an existing beam having the following data. B is equal to 350, D is equal to 900, D dash is equal to 50 mm, tension reinforcement of 5 20 mm HYSD bars of Fe415 and compression reinforcement of 2 20 mm HYSD bars of Fe415 steel, and the grade of concrete is M15. So given data, the breadth or the width is 350 mm, the depth is 900 mm, and D dash is the so we can draw the cross-sectional diagram of this beam section. So we have the effective depth is 900. The width of the beam is 350 mm. The compression reinforcement, this is D dash. D dash is equal to 50 mm. And there is, how many bars are provided in the tension zone? We have 5 bars. So 1, 2, 3. We have 5 bars in the tension zone. And we have 2 bars in the compression zone. So there are 2 bars of 20 mm dia, and there are 5 bars of 20 mm dia in AST, and this is ASC. So this is a diagrammatic representation of the given problem. There is a doubly reinforced beam section. The effective depth is 900 mm. The width of the beam section is 350 mm. The depth of the compression reinforcement from the compression fiber is 50 mm from the top edge. There are 2 bars of 20 mm diameter in the compression zone, and there are 5 bars of 20 mm diameter in the tension zone. The Fy and FCK values are given, that is 415 Newton per mm square and 15 Newton per mm square. HYSD bars are high yield strength deformed bars. So first let's calculate the value of AST, that is 5 bars and the area of each area of cross section for each bar is pi by 4 d square. So 5 bars, so 5 into pi by 4 d square, d is 20, so 20 square, we are getting the value of AST. Going to ASC, there are 2 bars of 20 mm diameter, so total value of 628.3 mm square. Now calculating the total tensile force, T value is 0.87 Fy AST. So this is the value for AST. Going to ASC, the compression zone. In compression zone, we have, so AST is calculated here. The value of AST in the tension zone, we are substituting for calculating the total tensile forces. When you go to total compressive forces, 0.36 FCK XUB plus FSC into ASC. So 0.36 FCK XU is how much? 350 into XU. We're going to calculate the value of XU. So we're taking 350, the width of the beam, and we have the value of ASC, and FSC is we have to calculate. So this is the value of CU, the total compressive forces. So FSC value can be taken from the code book in SP16. It's a handbook in table F. So we are going to get the value of FSC. So here we have D dash by D. We have to calculate D dash by D, and for Fy value we have 415 and FCK is 15. For a doubly reinforced section, the compression reinforcement FSC, stress and compression reinforcement FSC in a doubly reinforced beam with cold deformed, cold worked bars. So here we'll get the value of D dash by D. So D dash value we have 50 by 900. For this value, for this D by D dash value and Fy, we have to find the value of FSC. So from there we are taking the value of FSC. So here we have to find the value of XU. So when we substitute the value of FSC, we are going to get this total value on equating CU equal to TU at neutral axis. Now we are going to get the depth of neutral axis of 182 mm. So XU max by D is equal to 0.48 for Fe415 steel. So XU max is, when you cross multiply D with 0.48, you are going to get the value of XU max. So XU max is greater than XU. How much we got XU? We got 182 mm and XU max is 432. So 432 is greater than 182 mm. Therefore, it is an under reinforced section. For an under reinforced section, the equation for MU shall be 0.36 FCK XUB D minus 0.416 XU plus ASC FSC into D minus D dash. On substituting all these values which we already have computed, the total moment of resistance of this section, we are going to get 473.3 kilonewton meter. So this is the first type of problem where the data for the cross section is given as well as the data for the steel provided is also given, and then we have to calculate the moment of resistance for a doubly reinforced section. So going to problem 2. Determine the moment of resistance of a doubly reinforced section given below. So all the data is already provided in the diagram. So this is the compression steel ASC and this is the tension steel in the tension zone AST. So ASC we are provided with 2 bars of 25 mm diameter. In AST we are provided with 3 bars of 36 mm diameter. The overall depth here we can see capital D is equal to 600 and B width is equal to 300. The effective depth small d is equal to 550 and D dash is equal to 50 mm. So all the geometric as well as reinforcement data is already provided in the diagram. So from there we can take all the data. B is equal to 300 mm, D is equal to 550 mm. AST provided, will calculate for area of steel we have 3 bars of 36 mm. So we'll calculate the total AST for 3 bars into pi by 4 d square, 36 square. When we are going to calculate, we are going to get 3054 mm square. Fy provided is 250 MPa and FCK is 20 MPa. D dash is given as 50 mm. So calculate the value of ASC. Going to XU max by D, the limiting depth of neutral axis from the code book for FE 250, we are going to get 0.513. So from here we get the value of XU max by multiplying D, and the depth of neutral axis, limiting depth of neutral axis is 292.1 mm. Now assuming FSC is equal to FST, that is 0.87 Fy, and considering a force equilibrium, therefore total CUC plus CUS is equal to TU. The total compressive force is equal to the total tensile forces. So CUS is 0.362 into 20 into 300 into XU. So here we have an equation in terms with XU. Similarly, we'll calculate CUS for steel. And we're going to get a total value of 204806 Newton. Now tensile forces, 0.87 Fy into the area of steel, we are going to get a value. Now we are going to put it in this equation. CUC plus CUS is equal to T, and now we are going to get the depth of neutral axis, which is less than the limiting depth of neutral axis. Limiting depth of neutral axis, we got 292.1 mm. So now the calculated value is less than the limiting value, therefore it is an under reinforced section. Hence, that we had assumed that FST is equal to 0.87 Fy is also justified. Now calculating the strain in the compression zone, we are going to get this 0.0035 1 minus 50 by 211.5. We are getting a value which is greater than strain in the yield strain of the steel, that is 0.87 Fy by epsilon. This is the value of the Young's modulus. So this is stress by Young's modulus. We are getting the strain, yield strain. So this is the total value. So FSC is equal to 0.87 Fy is also justified, which is greater than 0.0109. So the ultimate moment of resistance MUR is CUCD minus 0.416 XU plus CUS into D minus D dash. Putting all the values provided and computed values, we are going to get the value of the limiting moment of resistance, that is 314.6 into 10 power 6 Newton mm, or it can also be called MP. So when we're converting into kilonewtons, we get 315 kilonewton meter. So let's look at another problem. Determine the ultimate moment of resistance of a doubly reinforced section for M20 concrete and Fe 415. The data provided, this is the overall depth, there is effective depth, there is D dash, and there is B is provided, the ASC is provided, and AST is provided. So let's look at the solution. B is equal to 300 mm, effective depth is 655 mm, cover for the compression steel from the compression fiber, top fiber is 45 mm, Fy is 415 MPa, FCK is 20 MPa. So ASC is equal to, we calculate the total area of steel of compression steel. So you're going to get pi by 4 d square into 2 bars in the compression zone. So this is the total compression steel. Coming to AST, we are going to get 4 into, we're taking 4 times. So there are 4 bars in the tension zone. So 4 into pi by 4 d square, we are getting 1964 mm square. Calculate the value of XU. XU max by D for Fe415 is 0.479. So taking that value, we get the depth of neutral axis. XU max is equal to 0.479 into 655. The value of D is already given. When you multiply with D, you're going to get the value of the limiting depth of neutral axis, that is XU max. Now assuming for a first approximation that FSC is equal to FST, that is 0.87 Fy. Now calculating CUS, so 0.362 20 into the width into XU. In terms of XU, you're getting the value of CUC. Going to CUS, when you go to CUS, we get 0.87 Fy minus 0.447 into 20. That is a diabar multiplied by 982. That is area of compression steel. So we are getting a value of compression steel. So this is the compressive forces due to concrete, and this is the compressive forces due to steel. So in the compression zone, we have concrete also contributing to the compressive stresses as well as steel. So when we are talking about compressive forces due to concrete, we are getting 0.362 into 20 into 300 into XU. And for steel, compressive stresses for steel, 0.87 Fy minus 0.447, 20 into area of compression steel. Going to the tensile forces, we get 0.87 Fy into area of steel, and we get a value. Now compute for equilibrium. Total compression is equal to total tension. So for the section to be in equilibrium, we are saying total value of compressive forces is equal to the total value of tensile forces. So equating the two, we'll get an equation to calculate the value of XU. So XU, we are getting 167.3 mm, which is less than the XU max value. The XU max value that we found was 313.7 mm. Since XU is less than XU max, that means it is a under reinforced section. So we are assuming that FST is equal to 0.87 Fy. Now calculate the value of the strain in concrete and calculate the value of strain in steel. Now epsilon SC is less than the yield strain. So FSC is equal to 0.87 Fy is not justified because epsilon SC is less than the epsilon Y, that is the yield strain of steel, whereby the calculated value of CUS, that is 167.3, may not be correct because this is less than the yield strain. The correct value has to be alternatively, you have to derive it by the strain compatibility method. So assuming epsilon SC is equal to 0.00256. So we're going to take the equation and put the values for, we're getting the value of FSC. Now CUS, in CUS we're going to put the value of FSC and get the total value of CUS. So CUC plus CUS is equal to TU. Equating this, we're going to get the value of XU. Putting all these values, we're going to get the value of XU, and it is the new value is coming up to be 173.8 mm. So epsilon SC, in this equation again we are going to put the value of XU, and we get the value of epsilon SC, that is 0.00256, which was already calculated earlier. Now we're going to try the iteration for the second cycle, now assuming 0.00259. In the same equation, again we're going to put the value, and the new value should be calculated for second cycle. The second iteration, we're getting 347.4 MPa. So CUS is equal to 347.4 minus 0.447, 20 into 982. We're getting the value. From here, we get the value of XU. So you get 173.4 mm, which is converging. So XU is equal to 173.4 mm. So now we're getting the ultimate moment of resistance, that is CUC into D minus 0.416 XU plus CUS into D minus D dash. Putting all these values, substituting the values of all the terms in the equation, ultimately we're getting the total moment of resistance, that is 422 kilonewton. So these are the references. So today we have discussed about problems on solving and designing a doubly reinforced beams. Thank you for joining.
Like, share and subscribe. Hit the bell icon for more updates.